Hi, my name's John Downing. I'm a limnologist and aquatic ecologist, and I'm the author of this set of sessions discussing various aspects of aquatic ecology and limnology. This session that we'll do now is called Stream Hydrology and Channel Structure. It's the 8th in the series of about 28 various sessions for aquatic ecology and limnology. I have several objectives for today. I'd like you to learn how hydrologic cycle drives streams, and we already have some sense of that from the earlier sessions where we talked about the hydrologic cycle and how it works and how it moves water downstream. We've talked a little bit about stream formation and flow and so on, and the various factors that go into that. But I'd also I'd like to go into that in some more detail. I'd also like you to learn how stream flow is related to climate and landscape, and we will discuss that to some degree. Learn the influence of landscape impacts on stream conditions. I'd like you to understand the geography of stream flow and structure, and learn how stream flow influences habitat and ecological conditions, and that we'll go into in some great degree. And then I'll learn the basic zones and structure of stream ecosystems. So here is an image from the new limnology book by Jakob Kalf. Actually, the date down there is wrong. It should be whatever that publication date is, certainly not 2002. But what I'd like you to see here is how the hydrologic cycle works in moving water. We've looked at this before in a grosser sort of scale. But here we have, of course, precipitation, the major driver of the hydrologic cycle, falling on the landform, and some of it running off and some of it infiltrating. It moves down through the litter layer and the root zone and the unsaturated zone, and moves down into the saturated zone, which includes the water table, is below the water table, and includes a surface or unconfined aquifers, sometimes an impermeable layer, and sometimes a confined aquifer. In general, the important forces here for stream flux is that water flows off, goes into the stream or river. It runs off as overland runoff or overland flow. And it also can flow versus move as subsurface runoff, but most importantly is groundwater flow. And at some point we'll be talking about base flow and peak flow. And when we talk about base flow, this does not mean base level. So please try not to get those mixed up. In the last session number 7, we talked about base level. That is essentially sea level. Base flow is the part of a stream flow that comes principally from groundwater. That's what the background flow is, irrespective of runoff or overland transport. Stream flow is related to climate and landscape in a very important way, and that is that if the landscape is quite modified or devoid of vegetation, then stream flow varies in a very different way and can be destructive to water quality and aquatic habitats. Now, what you're seeing there on the left-hand side of this is called a V-notch weir, and that's one of the things we use for measuring flow. Basically, the more water flowing down through that stream, the higher will be the position in that V-notch, and making measurements on it will tell us how much volume is flowing through there, and if we measure then velocity and so on, well, we can actually relate that using a thing called a rating curve to the flow rate of water, because the physics of it are quite clear and straightforward. That's what we use for measuring flow rate. On the right-hand side of the screen, you see a plot again from the Kalf book showing discharge and precipitation. Precipitation is this gray stuff here, and discharge are these various lines. Now, in sort of a normal sort of watershed, a forested watershed, or an area with good grasslands or prairie or something of that nature, what happens is that over time we get a rainfall event. This is a high-intensity rainstorm. Now, This is base flow down here at the bottom, and that's the amount of flow in the stream that comes simply from that discharge of groundwater. Okay, so base flow is down here. So as the storm intensity increases, that water begins to gather up, driving up the stream flow, and we eventually come to a peak discharge rate, a rate of discharge, usually measured in something like cubic meters per second or something of that nature, and that would be discharge. It's not the same as velocity. It's the amount of volume that is going downstream per unit time. This is the peak discharge, and then a fairly long tail to that curve as the wetlands that have filled up from the storm begin to discharge their water and so on. So this is kind of a standard kind of unperturbed watershed, has a discharge rate that is, the peak comes far after the storm, and it is not terribly high. If we have a clear-cut watershed or an agricultural watershed that's been greatly modified, then here the base flow is going to be lower because there's less groundwater recharge. And after the storm, the peak comes up very rapidly because there's not much retaining that water in retaining that water on the landscape because we have taken away the vegetation, often drained the wetlands, and decreased any kind of retention structure. Plus, we have much less groundwater infiltration and much more runoff. So base flow is reduced and peak discharge is greatly increased. Now, we'll be talking a little bit later in this session about the effect of flow rate. When the discharge is high, the velocities are high, and a lot of sediment tends to move downstream, and that can be destructive in several different ways. After the peak discharge is reached, the curve decreases really quickly because, again, there are not that many retention structures upstream, and so there's very little to be emptying out. And this is what we call a flashy watershed. We get flashy watersheds such that when there is a high-intensity storm, the there's very quick transport of that material downstream, and it can actually be quite dangerous in forming things like flash floods and various problems of that nature. So very different. Stream flow is related to climate and landscape. Obviously, the more storms we have and the higher the intensity of the storms, the more we'll tend to get high peak discharges. But definitely the configuration of the watershed is very important in retaining water and keeping us from having very, very high, quick flashes of flooding downstream. There are several measurements that we make on these kinds of hydrographs. This is called a hydrographic curve. Here we have time again. Here we have discharge, as we saw before. And here's a precipitation rate on a different graph. And what we have here is base flow, which is mostly supplied by groundwater, base flow over here once the effect of the storm is over, and then a lag time, which is the time differential between the peak of the storm to the peak of discharge in the stream. We have a rising limb up to the peak and a falling limb, and the storm runoff is also plotted, but basically the storm runoff is the difference between the base flow and the overall flow, is this area beneath here. Rising limb in a modified environment, the rising limb will go up quite quickly and come up to a very high peak, whereas in a less modified habitat, it will increase less quickly and go to a lower peak. The falling limb in a less modified habitat tends to be very slow and tail off over a long period of time due to all the retention structure in the watershed. Those are the important parts of a hydrograph, important to know and remember. The shorter the lag time and the higher the peak discharge, then the flashier the stream. Now, defoliation has a big effect really on stream condition, And this is, again, a sort of an overall look at what happens when we cut away vegetation and alter habitats. And I'll just sort of walk through part of this, most of it with you, that when let's say we clear cut or clear away vegetation, we change the environment pretty substantially. Now, over to this right-hand side, what have we done? Well, we've reduced the ultraviolet radiation barrier to the stream by taking away tree cover, and we have decreased transpiration excuse me, substantially, transpiration by trees and other vegetation. And we've also, because we've taken away the vegetation, we've decreased the nutrient uptake quite a lot. So many things happen. Now, because of the ultraviolet radiation barrier being reduced, we've increased stream discharge and increased the impinging ultraviolet, which keeps some kinds of organisms from growing. Because transpiration has been markedly reduced due to cutting away of vegetation, then we also have increased stream discharge. Now, the effect of decreasing nutrient uptake by vegetation on a landscape is, of course, increase of dissolved substances in soil solution, and that makes it possible to have substantially more nutrient transport downstream. On this side of the curve, the clear cutting or reduction or modification of the environment has led to increased radiation to the soil. This has created warmer and moister soil, which is warmer and moister soil, which has increased rates of decomposition, mineralization, nitrification, and so on. And this has an effect on dissolved substances in the soil. And this, plus the new flow of water, accelerates loss of dissolved and particulate nutrients and organic matter downstream. And the clear cutting or change in the habitat then can have multiple effects: increased discharge, increases in sediment erosion, and increases in nutrient transport downstream. These things occur in wherever we modify habitats to a great degree, either by cutting away of trees, cutting away of vegetation in prairies, mowing, but also by increased agricultural development, and also cities have the same kinds of effects because of the decreases in vegetation and permanence of vegetation. There is in extreme defoliation and loss of cover leads to extreme effects, and here's a little cartoon showing all the things that go on in agricultural ecosystems, but most of the changes lead to nitrogen, phosphorus, and silicate transport downstream, large amounts of sedimentation and impoundments, and a terrific amount of nutrients that move down to subsequent ecosystems, including marine ecosystems, and this can have huge and detrimental effects for aquatic systems all along the entire route of the hydrologic cycle. Precipitation and stream flow, of course, vary with latitude, and precipitation definitely varies with latitude, and that's the upper dashed line here that you see, P sub V. This upper part of the graph shows you precipitation. This other part of the graph is evaporation. And of course, the difference between precipitation and evaporation here is a net water surplus. And in some places we have water deficits, notably in the desert regions of the latitudes. Around the equator we have a substantial surplus of water, so we have a lot of aquatic systems, for example the Amazon River and others that are around equatorial regions, but also in the north and south temperate zones. There's a fair bit of water moving in streams. One can calculate runoff based on precipitation and evaporation is a very clear function of temperature. Therefore, I think you can imagine what the effect of climate change on the patterns of river runoff and river and stream runoff might be in future. Stream flow in tributaries is also important to lakes, and here we have Q. Q is almost always the discharge rate, and we see the discharge into a lake being less and less important over time with some sort of climate or watershed change. This drives down the chlorophyll concentration, here measured in the dashed line, and so the less input into that system, then the less nutrient and the less chlorophyll that grows there, and this can have a substantial effect on the productivity of downstream aquatic ecosystems. Sometimes it's very good to have some nutrients, especially in nutrient-poor areas, and so decreases in discharge into the lake, in this case, are a bit of a negative effect because the chlorophyll concentration will support less other animal life and less biodiversity in that system. Low-order streams are really susceptible to climate and landscape, and we've been through this in previous sessions, so I won't review it for you again. This is a standard sort of a stream order diagram, but the low-order streams, because they're catching the first flush, often are quite susceptible to these landscape and climate changes, whereas large aggregating rivers downstream are less so. There are many consequences of stream discharge and velocity, and one of the really important ones is a change in sediment quality. And I've said before in this series that if you look in a stream and look at the size of the materials that are deposited in the stream, it gives you a very good idea about what the flow regime has been like there. And this is an overall graph showing velocity against the grain diameter, that is our grain diameter of materials or soil and other geological materials that are either deposited, transported, or eroded. And I think you can understand this pretty well by thinking maybe yourself cleaning off a sidewalk with a hose, and let's say let's say a driveway or some kind of sloping surface. You want to clean off some kind of soil particles that are there. You'll notice that if you run the water very slowly, it doesn't really move very much. But if you speed it up by putting a nozzle on it that creates a high velocity flow, you can clean off the material pretty easily. And this is kind of the principle behind pressure washers, is that you increase the velocity and therefore increase your ability to move larger and larger particles. That's basically the entire story behind this particular graph. Now, so if we're looking for transport of a particular particle, let's say sand grain, we can see from here that sand grains will be deposited at velocities up to about this level, which is about 2 centimeters per second. After that, they'll be transported, and after that, they'll actually be eroded from bottom materials and carried downstream. Likewise, if you go up to gravel or even very large size gravel, this is a grain diameter of 100 millimeters. 100 millimeters is a really big, that's a 10 centimeter particle, which is, for those of you who don't do metric system, that's about 4 inches. So it's a pretty big stone here. That even a very large stone, it will be deposited up to a velocity of about something like 200 centimeters per second or a couple of meters per second. But after that, even that very large stone will first be transported, and then it'll be eroded from the system. What you see in a stream is basically what has not been washed away, and so the consequences of stream discharge velocities are huge for sediment quality and therefore habitat. Clearly, if you change the landscape around a stream, then you'll increase the peak discharge, you'll increase the velocity, and increase the amount of material that you will erode. Now, that may create a sort of a clean environment upstream, but all that eroded material eventually will slow down slow down to the point at which it'll be deposited again, and the silts are deposited very silts are only deposited at very low velocity, so you actually can silt in various environments by transporting these smaller particles downstream. Lots of things happen when the gradient is low and the order is high, and that the discharge gets to be very high. The velocity is low. Sediments tend to be fine, and channels have bigger meanders with a lower gradient, and seasonal variation in water flow leads to flooding and wetlands and very large floodplains. The stage in stream formation and landscape and climate influence a variety of different factors, including water velocity, annual flow regime, the permanence of streams as substrate, and habitat diversity. Hydrology means that stream structure is quite predictable, and this is a fairly bad graphic. I'm sorry about that, but it shows overall a cross section across streams at various places, and you can see by the bright blobs of blue, that's where the velocity is maximum. And if we cut through the stream here at this river bend, this would be on a meander, and look at the stream structure from A to A prime, you see that the high velocity is over here by the arrow. And also note that it's not at the top and it's not at the bottom. The highest velocity is somewhere between the top and the bottom, and this is called, where you find the high velocity is called the thalweg, Thalweg, thalweg. Okay? As this stream meanders, that area of high velocity, we go into, say, a riffle or run situation. The thalweg is not at either side because there's a lot of drag at the sides. It's not at the surface because of the drag there, and it's not at the bottom. It's somewhere in the middle. Again, the thalweg is in the middle, and that's the area of high velocity. This was used, I've been really interested in the fur trade in North America, and if you were canoeing up this stream, you'd want to pay close attention of where the low velocities are, because you want to cross them and not be in the high velocity part of the stream. Obviously you need enough water to float your boat, but if you're going upstream and you're paddling, you're going to want to seek the opposite of the high flow rate areas. And so the fur traders from Quebec or from Nouvelle-France knew this very well and would harness the hydrology of stream structure very effectively. It's very predictable and very interesting to study, as we saw in the last in one of the last videos. Pool and riffle structure are a characteristic of meandering streams, and this pool and riffle structure will vary with the flow rate and tends to sort of disappear when the flow rate is high and the stream becomes pretty much a riffle. But again, streams tend to meander. You have areas of deposition of material, and you have pools, which are deep areas, as we'll see in just a second, riffles, and they alternate with pools. And over here where you have the lower flow velocities is where you have deposition of material. And then over here you'll have erosion around the pools, and then transport of that material over here to deposit again. Now in reality there are different degrees of stream structure and different kinds of habitats that are fairly stereotypical. And so I'd like to show you a brief YouTube video from this group in Canada who's been working in this area, quite a bit in this area.
This video demonstrates how to recognize basic flow habitat types. A riffle is a shallow section of stream where the water flows over coarse streambed particles that create mild to moderate surface turbulence.
She's exercising her left arm, apparently.
The water's depth will be less than a half meter, and the velocity will be greater than a third of a meter per second.
You'll see soon that she uses an orange as an effective tool. Oddly enough, an orange is a very important hydrological tool in some areas, just showing that you can do hydrologic
pool
work.
is a reach of stream that is characterized by deep, low-velocity water and a smooth surface.
She's showing you over and over
the depth
again.
will be greater than half a meter, and the velocity will be less than a third of a meter per second.
The orange is not moving.
Runs are long, relatively straight, low-gradient sections of stream without flow obstructions. The stream bed is typically even, and the water flows faster than it does in a pool. The depth will be greater than half a meter, and the velocity will be greater than a third of a meter per second.
Pretty soon we lose her to high flow conditions.
A glide is a section of stream with little or no turbulence, but faster velocity than pools. The depth will be less than a half a meter, and the velocity will be less than a third of a meter per second.
There we've lost
A
her.
rapid is a section of stream with swiftly flowing water and considerable surface turbulence. Rapids tend to have larger substrate sizes than riffles.
I guess they do.
A fall is a high gradient drop in elevation of the stream bed associated with an abrupt change in the bedrock. A cascade is a short, high gradient drop in stream bed elevation, often accompanied by boulders and considerable turbulence.
So those are some important terms to remember. I'll let the credits run to give them credit for the fine little video and the sacrifice of the demonstrator to the rapid environment. I believe that was Tamri Hamill. So diverse kinds of habitats. The pool-riffle alternation is sort of the classic. Add to that the run, the glide, and then the very dynamic environments, cascades and falls. A variety of different kinds of stream habitats, all really derived from the hydrology of the system as well as the landform. Here's a really simplified view of the pool riffle environment. There are a couple of other terms here that are worth learning. Maximum depth is self-explanatory, but bankful width is the breadth of stream from the top of one bank to the other, and at sort of normal high flow conditions. Stream channels can also turn into lakes, and we'll talk about that quite a bit more later when we're talking about lake formation. But here we have sort of an old age meandering river, and I think you can see easily how these meanders can be cut off. You can look at Google Earth at any slow flow meandering stream. You'll begin to see oxbow lakes, but they can. But the point here is that as this river evolves, if we leave it to its own devices, this meander will get cut off. We'll start a new new meander, and so on. Rivers tend to migrate and change over time. Here's just river courses can change, and you can find this on historical maps. People get really annoyed with rivers taking over their towns and changing in position. This was true in this site in Santa Cruz, California. Here's where the old river used to run. They channelized it, made it nice and neat, so that it really wouldn't impinge on businesses and residences. Unfortunately, of course, that runs more water downstream and causes hydrologic issues downstream because, of course, anytime we straighten a water course, we increase the velocity, we increase head cutting, increase down cutting, and sediment transport, as we have learned in past sessions. Rivers and streams build very structured valleys, and you can look at any broad valley that you'd like that has a stream running in it or a river running in it. We'll have a variety of recognizable areas. These will be the channel, of course, where the river is running, and the floodplain. This is the big flat area on which the flood spreads out when the spring or monsoons drive it. There will also be abandoned floodplains or terraces that you find due to different periods of flow regimes, and then hill slopes. Hill slopes are also self-explanatory. The valleys can be quite wide when you have a fairly old river that has meandered broadly through that channel. Now, the wax and wane of floods out on these floodplains does a variety of different things, but one of the important things it does is it builds a structure and a structured kind of form called levees. Basically, you can visualize this water surface increasing, spreading out across the floodplain, leaving some of its sediment load there, and then receding back into the channel. And this will leave beautiful alluvium out on the floodplain, often very good farmland, but it also will give you some structure that looks almost human constructed around the channel of the river. Basically what happens is, and you can, there are several good videos out there on how this happens, but basically when the water flows out over the banks, it leaves the larger particles toward the edge of the banks, and the smaller particles spread out over in this area. And then as they recede, as the waters recede, you tend to get more sedimentation around the edges, and much larger sediments, coarser sediments, less easily moved. And so you build up a thing called a levee around the river. And levee in French means lever. Lever means raised, or it's lifted, and so you have lifted places. We build levees, but there also are natural ones that tend to keep rivers within their banks. Here you can see a couple of these. Those of you who read Chinese can read this part here about how the river itself can rise up above the floodplain if sediment deposition is enough. But over here you can see the natural levees around a stream. This is a system in very deep flood, but the levees remain dry land around the river course. So a summary of Session 8, quite straightforward. Hydrologic cycle. The hydrologic cycle, of course, drives stream dynamics. Without flow and water, you would not have any changes in streams. Stream flow is related to climate and landscape because landscapes that are more altered tend to give very different kinds of stream flow hydrographs, and climate, of course, has an effect because of the supply of water. Impacted landscapes then have really flashy streams with very short lag time between storm peaks and the high peak flows. Defoliation and stream flow influence the condition in the stream, of course, and alter the kinds of sediments that are in the streams and the kind of sediments that are moved downstream. Stream flow varies predictably across latitudes, and it does so because of the difference between precipitation and evapotranspiration, and probably will vary quite predictably with climate change. Streams and watersheds are very important to lakes also because they're a great supply of nutrients and water to those systems, and also flush out materials in the lakes and ponds. Stream flow influences habitat and ecological conditions, and does so by altering the sediment type due to the velocity of stream flow, and also does so by influencing the sediment deposition and where it's deposited, and what kinds of places silt is deposited versus larger rocks, gravel, sand, and other kinds of larger substrates. Stream structure is quite predictable, and it's related to meandering. Rivers are very interesting environments, and I hope this session has helped you to understand a little bit more about them.